So now that we've defined the Hamiltonian for the system, and we've kind of buried all that complexity into this angular momentum squared operator, so L squared over 2I, this is our Hamiltonian, right? So remember there's a second derivative del squared operator built into that we're kind of lumping into this L squared operator. And so this looks deceptively simple, right? Oh, it's just L squared over 2I psi equals E psi. But that includes all those fractions and derivatives that are part of the L squared operator. Now, again, somebody else already solved this problem. And so actually this set of solutions has a name. So the solutions, the wave functions that are a solution to this are known as the spherical harmonics. And that's sort of the terminology we give them. And we write them as y, l, m, and that depends, of course, on our angles, theta and phi. And so we have two quantum numbers. L and m. Sometimes this is also L and m sub L, because m depends on m sub L. And one thing to note is that m sub L ranges from negative L to positive L in integer increments, and these are both integers, just like all the other quantum numbers we've come across. Okay, and so this set of spherical harmonics, I've got a plot down here of what they look like. These may look familiar. So these are the different L and M values. We have y0, 0 here is the most basic spherical harmonic. I'll color in green. So y0, 0. This looks like just a sphere. And so, remember, this is at a fixed length, right? R is fixed. And so what this is representing is how does our function change as a function of angle. So red indicates positive, blue indicates negative in this case. Nope, it doesn't. Scratch that, because the y00 is just equal to 1. It's just a sphere. All right, so for some of these other ones, it has positive and negative parts to it. So y01, there's a positive part on the top, negative part on the bottom. And what we see here is what we call a node in the middle, right? So there's a node right in between these. And these may look familiar because these look a lot like hydrogen orbitals. And what we'll see in the next chapter when we talk about these in a little bit more detail is that these are directly related to the orbitals of atoms that we're used to seeing. So this is, this is an s orbital. These are p orbital. This is a p orbital. Here's a d orbital. Here's an f orbital, right? And so, or actually a different d orbital. This one's an f orbital, and this is also an f orbital, right? And so you've seen these before, right? These solutions, but these are also the solutions just for the rigid rotor. And so this is sort of what they look like. And we see, nodes here. We get a different angular node here. So we have nodes as well. And this is sort of what these functions look like in three-dimensional space.